Okay, thank you. One more announcement. People who take the van to back to the hotel, the van will be here at 7 o'clock after the reception. So I like to present Jiagang Yang from Universidade Federal Fluminense, who talk about measure of maximal u-entropy for map data factor over Anosov. Thank you, Janeiro.
I would like to thank the organizer, the invitation to give a talk at the conference of Marcelo's birthday. I entered IMPA in 2005, so during the last 17 years, Marcelo always not just teaching, also commending very important orientation to us, and for his help and for our relationship. So I would like to talk one result of our part of our recent working process in the last 5 or 6 years. It's about maximal u-entropy. So we started from for partial barbodic diffeomorphism. Partial barbodic diffeomorphism means we have two bundles. One bundle is uniformly expanding. So for the stable manifold theorem, we have the unstable bundle. The unstable bundle is uniquely integrable, so we have the unstable foliation. We would like to understand what happens for the unstable foliation. So one part is, it's quite simple for foliation theory. It looks like nothing to study for foliation theory by two reasons. The first reason is that the topology of the leaf is quite simple. It's RD. No topology in every leaf. On the other hand, the volume growth speed is only polynomial. This was, I think it was first proved by Gromov for the expanding map. When he classified the expanding map, he showed that the volume growth is a polynomial, and then they showed the manifold is near manifold, something like that. But here we have a similar result to show that every leaf, the volume growth is polynomial. And as soon as we have the volume growth is polynomial, then we have the plant's result show we have a transverse inverted measure. So this means this foliation is quite simple. But on the other hand, for the dynamic system, it's quite complicated. It means it's defined by Sagin and Jeff Shah. We have uniform expanding, so they define the topological entropy. Topological entropy for the foliation means you take any small disk in the leaf, you do the iteration, dynamic iteration go forward. And now this volume increases exponentially fast. We can see the difference with here the volume is no dynamics. It's one fixed leaf. You see the volume, no iteration, it's polynomial. But if for dynamics, we see that the expanding is exponentially fast. So we try to understand what happens between the two differences. And in particular, we are trying to understand the following question. For partial barbodic diffeomorphism, we would like to see the dynamic behavior along the transverse direction. Because for foliation theory, we have a transverse inverted measure. So we are trying to understand what happens for dynamic system after iteration. So we consider any disk contained inside the unstable leaf. We do the iteration. This iteration, remember, the increase, the volume is exponentially fast. So principle, the intersection number of the image of the disk with the transverse disk will have exponentially fast numbers. We are trying to understand the distribution on the transverse direction. So let's see a simple example. We start from the small solenoid. Small solenoid is, we consider solid torus. So small solenoid will be, okay, let's see the picture. The small solenoid, they will rotate twice. So on the circle, we have a map, uniform expanding map A theta with degree 2. And on the vertical direction, the disk is uniformly contracted. So this is small solenoid. What we are trying to understand is we are trying to see what's about the stable formation, what happens. The same question. We are trying to see the distribution of the iteration. The first observation is if we see the one-dimensional circle, one-dimensional map, uniformly spanning, and we take one point, we see its preimage. Here is its preimage. The preimage converges to the maximum entropy measure, exponentially fast. So yeah, okay. I don't know if there exists some standard proof or not. We follow this I think can be proved follow a proof of a coupling technology by Dr. Biat. Okay, his proof about the most contracting. And so now we can ask about the stable formation. The stable formation for the small solenoid is a disk, vertical disk. And we consider d theta is a stable disk with its preimage because we need expanding. Expanding is we need to take its inverse map. And we see the preimage intersect with the disk. On the transverse direction is a disk, there is a circle. And the intersection will be exactly the same as above. Okay? So we know that at least for solenoid, the stable manifold, stable disk go backward, is expanding exponentially fast. On the transverse direction, its distribution converges to the maximum measure. So we are, of course, this is one simple example show maybe the maximum measure will play some role in the study of the transverse dynamic behavior of the unstable formation. But here, this formation, this intersection is, okay. The next page has not so many relations with our talk, but it's interesting. Is this formation, if you take this stable formation, is corresponding to a formation called the Hertz formation. Hertz formation is it is solenoid, you remove its image, and then you do some Cauchy space, Cauchy map. You identify a small circle with a big circle, this small circle with another big circle, so you get a Hertz formation. So the Hertz formation, so you have one circle, you have two preimages. One is red, another is green. So this is exactly corresponding to the two branches. So this result will show us for the Hertz formation, these circles, its preimage will converge finally to the maximum measure. Yeah, it has nothing relation with our talk today because this Cauchy space is a Hertz manifold. This leaf is one leaf, so this leaf is not RD, and it's not expanding, but it looks like quite interesting. Okay. So that's why we put it here. So in general, our aim is we are trying to build the relation between transverse objects. First is about the invariant transverse measure, which from formation theory, because every unstable as we said, unstable leaf, the volume growth is polynomial. So by Planck's result, is this invariant transverse measure. The second part is about the heating measures. The heating measures is we do the iteration for the unstable disks. They will cross the stable leaf. This quite looks like when the Thurston has studied the train track for the surface. He defined the heating measure. On the dynamic, we can also define the heating measure. And also, we would like to study the cohesion of some invariant measures under this formation. Why? This is exactly we observed this by the small solenoid. Small solenoid, remember we have a maximum measure, we do the cohesion along the formation, we get a measure on the circle. The circle is a cohesion measure. So the first part is from the formation theory on the transverse direction. The second part is the heating measures. We are trying to see the limit. And the last part is from the ergodic theory. We have a measure, we give a formation box, we see the cohesion or by Jokin's cohesion on the transverse disk. we are trying to see the relation between these three objects. We have some quick, naive observations. First, we should be careful about the quotient measures. Because by the Big-Hoff-Algorithm theorem, all the measures, they should live in different unstable leaves. So this means that if we do the quotient of different algorithmic measures on the transverse direction which are similar to each other, this means that if it works, we have at most one measure, it can work. Because for two different measures after projection, we are similar to each other. If one works, the other measure should not work for us. So as what we said, it looks like the maximum measure should be a good candidate measure for us to study the transverse dynamic behavior. But we have another problem. The maximum entropy measure, as what we did for small solenoid, it may be carried by a local Horseshoe. It has no global dynamic information from the unstable formation. It may be by a small Horseshoe. Why? Because we are not, for small solenoid uniform hyperbolic, we are at the partial hyperbolic. So what we have to do is we need a measure which shows global dynamic system, which we call the U. That's why we are not going to use the maximum measures. We are going to use measures from maximum U entropy. What's the U entropy? Okay, sorry, I have to use some notations which is not easy to explain. So when we have a foliation which is uniform banding, then as a standard work of Legendre and Legendre-Lessian, we could, or maybe pacing, we could define entropy along one foliation or lamination. We need to define a partition, which is a measurable partition, adapted, subordinated to the unstable foliation, and we need to define the conditional entropy. Sorry, I wanted to give the precise definition, but you have some kind of entropy along this direction. This is a U entropy, and we need the measures, which are measures of maximum U entropy. It means that our entropy for this measure equal to the topological entropy defined by Radu and Jevsha. This is called the measures of maximum U entropy. So essentially, we do everything along one direction. A good news for us is by Hua, Hu, and Wu, we could show that the measure of maximum U entropy is not empty. It's a convex space, it's compact, and every extreme point is ergodic. So this is exactly the measure we are going to use. We are going to consider this measure, do the quotient along the transverse direction, and we are going to show this projection measure will give us topological information of the foliation after regression. So our game. So our main goals are the following. We are trying to understand the structure of the measure spaces. We would like to know when the space is a finite dimension. And we would like to study the statistical properties for these measures, the decay or correlation, some other steps, center limit theorem. And we would like to understand the relation of the measures and the topological information of the strong unstable foliation, means the dynamic information on the transverse direction, like the transverse invariant measure and the Haiti measures. So modified by the small solenoid, we are going to study one special class of maps called the factor of Anosov. What's a factor of Anosov? It means this system is semi-conjugated to a linear Anosov. It's a semi-conjugated to a linear Anosov. And this semi-conjugacy, it maps every strong unstable leaf to unstable leaf of A, and center stable leaf go to a stable leaf of A. It looks like we have, this hypothesis is very strong, but indeed we have plenty of examples. We are going to explain a little bit. And this example is not, people will think it looks like Anosov, but it's not. Some systems can be quite away from Anosov. A little bit later, I will going to explain several family of examples. Of course, this is a working process, so we are trying to generalize this result to more general situation, remove this hypothesis. So for these systems, first we are trying to understand what happens for the measures with the maximum u-entropy. So we are going to explain reverse measures. The reverse measure is you map every unstable leaf of F to an unstable leaf of A. So we can, because this is a homomorphism, we can put it back the bigger measure for linear Anosov to the sum measure for F on the unstable leaf. So this measure is by semi-conjugacy. We take the linear Anosov, the bigger measure on the unstable leaf of A, we take it back. We get a measure. This measure is not the probability measure, but we have a measure. This is called a reverse measure. So we need to define a C-Gibbs state. C-Gibbs state is different with Gibbs state. Its definition is any measure is conditional measure along the unstable leaf is exactly the same with the reverse measure. This measure is defined by Marcelo. He gave a name for the C. It means that the Jacobian is a constant. And okay, so this is not, it's a little different with traditional Gibbs state. It just means the conditional measure should be our reference measure. So our first theorem say if it's factor of Anosov, the measure of maximum u-entropy, we know what it looks like. It's exact if and only if it's C-Gibbs state. Okay, so we know what it looks like for these measures. And then now we are trying to show the finiteness. Now we need a hypothesis called seamless contracting. Seamless contracting means for the reverse measure, if this is a positive measure subset, we have contraction go forward. This hypothesis, it comes most contracted center. It was first appeared in one paper of Marcelo with Chiang in one paper 2000 to study physical measures. And later, it appeared that most contracting in a different context. Most contracting has some very deep relation with dynamic system and with foliations. For instance, for harmonic measures, for foliation, conformal foliation, if without the transverse invariant measure, people could show there exist only finite many harmonic measures. That proof is using that similar technology with most contracting. And for physical measures, so seamless contracting is essentially quite a general hypothesis. So here we prefer to use a similar hypothesis, a seamless contracting center. So we have some weak hypothesis along the center direction. With this hypothesis, we could show we have a finite many algorithmic maximum U measures. So we have the finiteness. And moreover, each support has a finite many kinetic component, and each leaf, which is the support, is a minimal component. The unstable leaf is minimal in each component. So it looks like strange because contracting hypothesis can give us the minimality of information on the support. Yeah. But this kind of results has appeared several times in the history. As what I said, for harmonic, for conform foliation, if it has no transverse invariant measure, it has only finite many harmonic measures. Every component is exactly minimal. It's quite similar. All these results, theory are quite different, but the theories are parallel one to each other. Okay. So, okay, with seamless contracted center, we have only finite many algorithmic maximum U measures. Okay, we have measures at hand. So now we are going to see what happens on the transverse direction for these measures. So we have transverse invariant measure. Sorry, this statement is a little complicated. Essentially, It means if you do the quotient of the maximum U measure along the ensemble direction, the quotient measure is a transverse event measure. Essentially here you see that, okay, you give any maximum U measure, you consider quotient, and you have a transverse event measure. But here we put some constant here because we have some problems over the Fourier box. We have several Fourier boxes, and each Fourier box you have a transverse event measure only inside the box. But if you have several boxes, you need to adapt it. So that's why we put some constant. Okay. So essentially, you could understand if you have a transverse event measure, no, you have a maximum U measure, the quotient measure will be exactly one transverse event measure. So this partially answers our question. It means if you have one measure, projection will be a transverse event measure. So this is from the algorithmic theory to Fourier theory. People will ask another direction. If we have a transverse event measure, can we go back to algorithmic event measure? We don't know. Okay, up to now, we don't know yet. We don't know happens what in general. It's, that's our next step to try to understand the relation between them. Okay, so this is if we have one measure in one Fourier box, we do the projection on the circle. We have a quotient measure. This measure is a transverse event measure, but only invert inside the Fourier box. If you have another Fourier box, we move to one box to another box. We need some constant. What happens? The next step is a little quite surprising result for us, is we can ask more. We know that we have asked if the intersection of iteration of one disk with the transverse direction, if they converge to the transverse event measure, the answer is true. If we take unstable disk inside the support of the measure, inside the support, not necessary to be regular. Just inside the support, you take the iteration, go forward, you intersect with a transverse disk. The intersection, you take the average of the intersection. This is the distribution. The distribution converges to the transverse event measure exponentially fast. The main problem here, why this result is strange, is about the exponentially fast. Because in the Fourier theory, in general, it's very hard for us to control the speed of the convergence. Okay. So you see, here implies that we have a very strange phenomenon. So at least for factor of Anosov, for seamless contract system, our previous three questions, three measures are exactly the same. So we have a transverse event measure. We have a transverse event measure. We have a maximum U measure, its projection. And we have a dynamic convergence over iteration over unstable leaf. All these three stuff, they consider to each other. The same, more or less the same. Okay. So this is, but of course, just for one special example, is a factor of Anosov. We are trying to generalize to more general situation. Okay, if we see that if you iteration one disk, it will transverse intersect with exponentially fast. Okay. For these measures, for this maximum U measures, we can give some classification about the statistic properties. We could prove the large deviation principle. We could show exponential decorrelations. Another interesting fact here is we only need to assume this system to be C1. We only need this system to be C1. Okay. We don't need C1 plus alpha. The main reason here is because our reference measure is very good. The CS holonomy between which preserve the reference measures. CS holonomy which preserve the reference measures, which can help us to reduce the irregularity. And then we could use Dog-Biat's company method for most contracting physical measures to apply for our C-gibbsfield state. So now let's try to show some examples, because people will always ask, okay, if factor of Anosov, how different with Anosov? Factor over Anosov essentially can be quite different with Anosov. For first example is derived from Anosov, which is actually the topic Rafael will give a talk this Friday. So we consider a linear Anosov diffeomorphism with string values, K1 less than K2 less than 1, and we have one dimension expanding. We consider any partial parabolic diffeomorphism in the same isotopic class with A, which is called the derival from Anosov, the general definition. And so the first result is from the Rafael. In his thesis, he proved every derival from Anosov is dynamical coherent, which is a factor of Anosov. No matter how you change, it's a factor of Anosov. Of course, it should be very different with Anosov. And it always has seamless contractile center. This was proved by Raoul Ures. Every map has a unique measure of maximum u-entropy, proved by Raoul Ures also. And of course, it's considered with the maximum measures. So every partial parabolic system in this isotopic class, which is a factor of Anosov. Okay, so this is our first class example. And then we show that every unstable leaf, iteration of unstable leaf will give us our, on the transverse direction, will give us our transverse invariant measure, and it converges exponentially fast. The second example is diffeomorphism with the circle 5 bundle. This is an example from a paper of Rafael. Oh, with Andy or your paper? Rafael's paper with Andy. We consider sorry, not yet. Okay, sorry. I first need to give the definition. We consider C1 partial parabolic diffeomorphism, which is accessible, and the dynamic coherent with one-dimensional center, and the center formation forms a circle bundle. So that's why I call the circle bundle. If we have a circle bundle, we could consider the quotient space. We need to assume the quotient space to be topological torus. We need a hypothesis, because on the quotient space we have a topological Anosov, but in general we don't know if it's a torus. Unless we assume it's a three-dimensional. In higher dimension, we assume it's a torus. So we call this map is PH1. For example, this is the result of Rafael and Andy. They said if we consider three-dimensional Yang manifold, any partial parabolic diffeomorphism on this manifold will verify all these previous above properties. So the center is always dynamic coherent, circle bound, accessible, and the quotient is a torus. So we will use this example to give to show our application. We see that this example is not exactly like the Anosov. We have circle bundles. The proposition is any C2 diffeomorphism with only one hyperbolic periodic point. That means with only one hyperbolic periodic point. For instance, you could consider the Heisenberg group. On this near manifold Heisenberg group, you get one hyperbolic periodic point. Then congratulations, you have seamless contractile center. It just means you consider the Heisenberg group. You create one hyperbolic periodic point. Even all the other directions on the center, you have the identity, but you have a seamless contracting. So in this situation, we have a seamless contracting, and you have a unique, you see, indeed here you have a unique maximum U measure. Okay, so this is our second case. An interesting question associated to the second question is if we could remove this hypothesis with one hyperbolic periodic point. We think, we tried indeed, that any parabolic diffeomorphism here, you have exponential convergence in the transverse direction. If without hyperbolic, without hyperbolic periodic point on the transverse direction, you have rotation. But we do guess, in this situation, every parabolic diffeomorphism on the transverse direction still has an exponential fast convergence. Okay. The last one is a topological solenoid. The topological solenoid was one example first given by Bonatti and Mindy and Jiagang Yang. It looks like a solenoid with the same, sorry. No, wait a minute. Okay, here. If we compare the small solenoid and the topological solenoid, what's the difference? They have the same shape. If the small solenoid, here the small solenoid will be a little different with the example in the beginning, okay, like the Hertz foliation. On the circle, we have a key times theta with degree k. And on the fiber, we have uniformly contracting this small solenoid. What's topological solenoid? Topological solenoid on the horizontal direction, we still have uniform expanding. But on the vertical direction, we don't have uniformly contracting anymore. The derivative on the center is between 1 over k and less than k. It's only parabolic. On the transverse direction, indeed, you could see examples with infinitely many sources. And we could show that in this case, it has seamless contracting also. Okay. And remember, in here, we could have infinitely many sources. So we have plenty kind of examples. We could show that really the factor of Anosov, even with some hypothesis, we still have plenty of examples. So here we need, let me try to re-explain that we should be careful about the maximum measure and the maximum measure. People would like to study the equilibrium state for her system, global system. But we should be very careful. Because for equilibrium state, for parabolic system, equilibrium state, like the maximum measure, which may come from local horseshoe. Local horseshoe, which cannot give us the global dynamic information. So that's why we prefer to see u-equilibrium state. U-equilibrium state, instead of use entropy, we use u-entropy. So we could ask the potential realized by the maximum u pressure along the unstable direction, and which makes sense for us to study parabolic diffeomorphisms. Okay, so I think, yeah, it's too quick, but I think I could, so this is a working process started 4 or 5 years ago. And before 2000, we meet almost every Friday at IMPA. Also, he is very busy, but he always gives time for papers. And after pandemic, so we only meet online. So this was, I think, the first time I visited IMPA to his office. And both of us are very exciting because we have almost 1 year to see each other. And I chose this picture because here you see that we have a pants here, exactly like the one part of Hertz foliation. So I decided to put this further here. And thank you, Marcelo, and happy birthday.
Thank you, Yang. Question or comments?
You went a bit fast with the examples. I want to ask if these examples are not dA, derived from Anosov.
DA?
And if they have more than one measure of maximal u-entropy.
Sorry, it means the map, the example is not DA.
Yes.
If you DA, the second class is not from Anosov. It's, or you say the fiber, it permit fiber of Anosov. The second example is a fiber of Anosov. No, it's a circle bond of times Anosov. If you are trying to ask it not factor over Anosov, then
It factors over Anosov, but it's not derived from Anosov.
yeah, the second one is the second one. This is not derived from Anosov.
Ah, okay. Okay.
And the third either. The third, okay, you could ask the third one is derived from solenoid. Okay, so the second example is not a derived DA. And indeed, you could ask, okay, we are going to write one paper, but it's not written down here. Is you could consider any local diffie. You consider a map. Any map, you see its preimage. Any map, you see its preimage, like a solenoid. You have uniform expanding map. You take one point, its preimage is the stable foliation. So for any map, you could see its preimage. You have some similar results.
Okay. Thank you.
More question, comment? Okay. Also, we thanks again to Jiagang Yang. And we back 4:15.